of this as we move along. The Vxlan gateway is an entity, allow non-Vxlan device to talk to a Vxlan device. So it just sits at the edge. So what is Vxlan? So Vxlan is a layer 2 overlay scheme. It's one of the layer 2 overlay scheme that runs on existing layer 3 IP network infrastructure. An overlay network is basically, so the Vxlan overlay network is actually used to carry MAC traffic, Ethernet traffic. So with Vxlan, so basically what happens is, being an overlay network, the original packet, is actually encapsulated, on the Ingress device. And, every device, along the path, is oblivious to what is actually happening. They just route the packet normally as they will route any L3 packets. When the packet gets to the egress device does the decapsulation of the packet, and then which now reveals the original payload, which then get forwarded, natively. So as I've mentioned, each of the overlay network is termed a Vxlan segment. So basically, like I said, a Vxlan segment, is akin to your broadcast domain. So only devices within the same Vxlan segment can actually communicate. The Vxlan segment is in turn identified using a 24-bit segment ID. So theoretically, that gives you 2 raised to the power 24, which is around 16 million. In theory, however, in real life, I believe most vendors actually support around 16K VNIs. So the VNI, which is the Vxlan network identifier, is part of the outer packet encapsulation. The underlay, so to make a distinction between the overlay and the underlay network is your IP transport, okay? And it just provides reachability between the endos, between the VTEPs, so between your PEs, so to say. This is a logical representation of the distinction between the overlay and the underlay network. So the physical network is your underlay here, and the overlay are tunnels. So that gets signals transparently between the your VTEPs. Your VTEP in this case are could be these are live devices. So Vxlan uses UDP port 4789, and what that gives us is the ability to have to use that as an entropy for traffic load balancing. So basically, the UDP destination, as mentioned for Vxlan, uses a port 4789, and then setting that the source UDP port to an hash value allows packet load balancing within Vxlan environments. So Vxlan VTEP paired discovery. Today, in the vanilla implementation of Vxlan, there is no VTEP auto discovery. So VTEP are the devices that does the packet encapsulation and decapsulation within the Vxlan context. So you have to manually define your remote VTEPs, essentially. So no auto-discovery within the vanilla VTEP implementation. However, with EVPN, that is actually alleviated with EVPN. Vxlan are end host devices discovery. So, as we have in VPLS, the original implementation of Vxlan actually relies on the data plane flood and learn. So the packet gets flooded. The Ingress devices learn the source MAC addresses, and as you know, the flood and learn comes with a lot of scalability issue, which is why with EVPN, again, EVPN is actually, written to actually overcome some of these shortcomings that we have in the native Vxlan implementation. Vxlan and multicast traffic. So again, with the vanilla Vxlan implementation, the draft actually mandated that the underlay network, supports native IP multicast. So in which case, you're going to have your PIM, your rendezvous points, IGMP and all those jars going in the underlay. And basically, that is needed to forward multicast traffic within the vanilla Vxlan environment. And the way that is achieved today is the layer 2 VNI is actually mapped to an IP multicast group. The VTEP then sends out the PIM join message expressing interest, and that's how you build your RPT tree. However, with the newer version of software running on, most of the vendors, they do actually support what they call the Ingress replication. So Ingress replication is also known as end-end replication. And basically what that does is each of the Ingress device, the VTEP, they build what is known as a flood list. So flood list is actually the list of remote VTEPs that I'm going to forward any bump traffic to. And the advantage of having Ingress replication is you don't need to have native multicast in the underlay again. So you abstract that the need to have a native, the underlay running native multicast. The downside though is, depending on the amount of multicast traffic, you might run into some scaling challenges, because if you have 10 odd remote VTEPs, it will mean the Ingress VTEP, and those are part of the same Vxlan segment, it will mean the Ingress VTEP needs to replicate that same single bump traffic 10 times and, and distribute each to each of the remote VTEP. From packet encapsulation perspective, this is what Vxlan packet encaps looks like. So you've got your outer MAC, which is 14 bytes. You've got your outer IP, which is 20 bytes. You've got your UDP packet, which is 8 bytes. And you've got your Vxlan header, which is another 8 bytes. So overall, you have an overhead of 50 bytes added to the original payload minimum. If we zoom in into the Vxlan header itself, this is what it looks like. The key is the flag, so the high, is actually set to 1 for a valid Vxlan network ID. Below, you have your 24-bit VNI, and the rest are reserved. As This is a sample topology of a lab demo. So basically, what I've tried to do here is to, walk you through some basic Vxlan configuration to show, how a client here can, talk to a client here, within the same data center or across the data center. It doesn't actually matter. As long as you have your IP underlay network configured properly. So from configuration perspective, this is a sample configuration snippet for my live devices. Again, the key is, so for the, for the VTEP, because there's no auto discovery, like I mentioned, this configuration is done using a Arista, VM. So because there's no auto discovery within Vxlan, so this is vanilla Vxlan configuration, no EVPN here yet. So you have to manually define your remote VTEPs, and these are defined there. Again, your VNI, which is globally unique, it needs to be globally unique. So this is mapping my VLAN 20 to this VNI, on this leaf. Again, the same needs to be done on the remote leaf as well. UDP ports, 4789, doesn't need to be specified. Now is the default on the Arista platform. And then, where am I sourcing my Vxlan packet from? Loopback 0. So you can see the IP addresses of, assigned to those loopback 0 in there. So from the client perspective, so basically, I'm just, using an SVI to demonstrate, the packet flow between the customer perspective here, using Vxlan. So your underlay network, again, here I've opted to use OSPF, as my IGP just to learn my loopback addresses. And from the client perspective, I've got connectivity, through just a native ping across. It is actually worth mentioning with the Arista, though, you don't actually see the VTEP unless there is interesting traffic. So that is, even though you have your configuration done, you do show Vxlan VTEP, you don't see anything. It doesn't mean it's not working. It just means, there's no interesting traffic flowing. So here, what I'm showing here is the MAC addresses being learned, from the remote. So you can see over the that VTEP, this MAC address is learned dynamically via Vxlan tunnel. This is the remote VTEP. And again, the same applies to the other side as well. And that concludes Vxlan. Any question on Vxlan before we move on to EVPN? Okay. This is where the fun starts. With EVPN, again, EVPN is, was designed to actually overcome most of the shortcomings of native vanilla Vxlan. So again, a lot of acronyms we're going to start with. So EVPN essentially is Ethernet VPN. You've got your EV high, which is EVPN instance. And basically, an EVPN instance actually spans multiple PEs, You've got your MAC VRF, again, which is similar to your IP VRF, but your MAC VRF actually holds your MAC addresses in this case. You've got your IPVRF, which, you used to today, which owns the native IP routes. DF is actually designated forwarder. So basically, this decides, if you have two devices, serving the same Ethernet segment, to avoid loop and duplicate traffic, only one of them is, allowed to send bump traffic back to that Ethernet segment. So we're gonna go through details of how the election happens today for designated forwarder. Your Ethernet segment. So Ethernet segment is basically your attachment socket, in simple word. So basically, when you have a client side that is connected, to more than one PE, that via set of Ethernet links, that set of links is actually called the Ethernet segment. So just think of it as your the sockets essentially. VTEP we already defined, which is your Vxlan tunnel endpoint, that does the encap and decapsulation of the Vxlan packets. NVE stands for Network Virtualization Edge. So this is the same as your PE or VTEP. It's just some acronyms, defining the RFC. The NVGRE is your network virtualization using GRE tunnel, basically. So again, that is another. So Vxlan is one way to carry L2 packet in the overlay. NVGR is another method defined. There's actually an RFC written by Microsoft on this. Okay, so with acronyms out of the way, let's delve into the Evpn overview. So as I've mentioned, why the native Vxlan draft, does not define, a control plane, which means, the native Vxlan now relies on the data plane flood and learn, which again, as I've mentioned, introduce some scalability concern. Evpn is meant to alleviate that for us. And so basically, Evpn, let me just move to the next slide quickly. So within Evpn, MAC learning actually happens, not in the data plane, but in the control plane. So here, the BGP, multi-protocol BGP is actually being extended, to carry MAC address, today. And today, the address family that is assigned to Evpn is the, the address family identifier of 25, which is the same that we use today for L2 VPN. However, the subsequent address family identifier, the SAFI, that is dedicated to Evpn today is 70. So with multi-protocol BGP in the control plane, that gives us a lot of advantage when it comes to implementing Vxlan. So one of the advantage, if you recall, with the vanilla Vxlan, there is no auto discovery. You have to manually define your remote VTEPs. With Evpn, Evpn, takes that away for you. So with Evpn, auto discovery is achieved. So Evpn provides auto discovery. The other thing we gain with EVPN is the unified control plane. So again, is BGP that pretty much we're all used to. Here, I try to go into some of the details of the advantages of using an EVPN. As I've mentioned, unified control plane is one of them. Reduction of bump, traffic flooding in the control plane, because now, BGP, is used within the control plane to achieve that for us. The other thing is the distributed layer 3 gateway. This we will come to in future slide. But most importantly, the ability to have a faster reconvergence now when linked to when your server is actually drawn to two leaves, for instance. Those are some of the features we're going to be exploring within EVPN. So the faster reconvergence is actually achieved with a feature known as mass withdrawal, which we'll come to in a bit. So as I've mentioned, EVPN actually has support for multiple data plane. Within the data plane, so remember the EVPN sits in the control plane. The data plane where is actually how the packet is actually forwarded, and that's EVPN leverages all the following. So all these are actually defined. So first is the Vxlan encapsulation, which we're talking about today. The NVGRA encapsulation is also supported. So these two actually means, that data plane allow, they sit on the vanilla IP transport. EVPN also supports MPLS. Actually, the initial draft, the original draft for EVPN was actually written around MPLS data plane encap. The implication of that is that mandates you to now extend MPLS into your data center, which a lot of enterprise are not keen to do. So which is why the Vxlan encapsulation in the data plane was actually the draft was written. And those values actually, so all these values, these are the values that's been allocated by IANA to for each of those encapsulation data plane encapsulation protocol. So these are carried as part of the BGP extended community, which I'll show you in a bit. So from data plane encap perspective, this is what the packet looks like. So again, as I've mentioned, EVPN can support MPLS data plane. It can also support Vxlan data plane, as well as the NVGRA. So from packet perspective, you've got your outer transport label. If the encap is MPLS, so in the middle, you've got your service label, and then at the end, you have your payload. For Vxlan encapsulation, you have your outer IP header, you've got your VNI ID, and you've got your payload. For the NVGRA, you've got your outer IP as well, because remember, both Vxlan and NVGRA actually runs on native IP transporter underlay. Next, you've got your NVGRA, the virtual segment ID. Again, this and this actually, they both are 24 bits. And then you've got your payload. So combining EVPN and Vxlan, again, as mentioned, EVPN, leverages multi-protocol BGP. As I've mentioned, the address family identifier of 25 and the subsequent address family identifier of 70 is been assigned to EVPN. It provides VTEP auto discovery, so again, now you don't need to manually specify your remote VTEPs. And the key also is, with EVPN, flooding is actually drastically reduced. We're going to come to this in a bit. The EVPN RFC actually defines a couple of service models. So service model essentially is how your VXLAN actually maps to your VNI. So three service models are actually defined in the original EVPN RFC. The first one is the VLAN-based service interface. The second one is the VLAN bundle service interface, or the port-based service interface. And the third one is the VLAN aware bundle services. So this it's got pros and cons. I'll come to that in a bit, but it suffices to say pretty much all the big vendors today only implement the VLAN-based services and the VLAN aware services. The VLAN bundle services, it's pretty much not implemented or not commonly implemented. So with the VLAN-based service, which is, again, remember the service model is just how do you map your VLAN to VNI. That's basically it at a high level. So with VLAN-based service, this has a one-to-one mapping between the VLAN ID and the VNI, sorry. So with, and what that gives you is the ability to have VLAN normalization or VLAN translation. So the remote VLAN ID doesn't need to match, The VLAN-based services gives you the opportunity to have a VLAN translation. It also allows you to have overlapping MAC addresses because each of the VLAN, it's sits in its own broadcast or VXLAN segments. The VLAN bundle service, as I've mentioned, is not widely implemented, so has a many-to-one mapping between VLAN and a MAC VRF. The MAC VRF consists of a single bridge table, and the EVPN instance, the EVI, corresponds to multiple broadcast domains. So here, the implication of that is you can't have overlapping MAC addresses. I actually have a slide that summarizes both the the comparison and pros and cons of each of these service models shortly. The third service model, which is the VLAN aware, with VLAN aware bundle service, here the EVPN instance consists of multiple broadcast domain, with each VLAN having its own bridge table. So the VLAN aware bundle is actually, takes the advantages of the VLAN aware and the advantages of the VLAN bundle, the bundle service, and combine it into one here. So this is the slide that actually, compares the pros and cons of those the service model. So as I've mentioned, with VLAN-based services, this is one-to-one mapping between the VLAN and the and the EVPN instance. And what that gives you is the ability to have VLAN normalization and the ability to have overlapping MAC addresses, because again, you know, each of the VLAN sits in a separate Vxlan segment. With the VLAN bundled is many to one, as I've mentioned, and the implication of that is that you can't have VLAN normalization, which is essentially VLAN translation. You can't also have, you know, overlapping MAC addresses. So each MAC address within VLAN bundle service needs to be unique. The VLAN aware is again end-to-one, many-to-one, and gives you the advantages such as the VLAN normalization or translation and the ability to have overlapping MAC addresses. Okay, EVPN route types. So the original EVPN draft actually specify 4 route types, so which we're gonna go through. There's been some additional route types defined, you know, I'll try to touch on those as well. So this is actually modeled on the back of point to multi-point next generation multicast, if you've done that in the past. So route type 1 is actually your Ethernet auto discovery route. So there are 2 types of these. The Ethernet auto discovery per Ethernet segment and Ethernet auto discovery per EVPN instance. And the usage, you know, some of the usages actually is the PE auto discovery. So this is how we achieve remote VTEP auto discovery within EVPN. You know, remember with VXLAN you have to manually define this. The route type 2 is your MAC advertisement. So again, this is your host reachability, layer 2 reachability information. This is how it gets advertised. So all these are encoded, you know, using BGP. I'll show you what the route looks like in a bit. Route type 3 is your multicast route for, you know, building your flood list. Type 4 is your Ethernet segment route, which is essentially used for Ethernet segment discovery and your designated forwarder election. Route type 5, although was not part of the original EVPN RFC, it allows IP connectivity, so prefix connectivity, so similar to your IP VRF, you know, multi-tenancy and stuff. So your type 5 is actually IP prefix, so yeah, and it's used to advertise IP routes. So I think the key here is in order to indicate which type of data plane encapsulation is used, so the BGP encapsulation extended community is included in all EVPN routes. So this is what I was saying. Remember those data plane encapsulation value with VXLAN set to 8? That is actually carried, as I've mentioned, as part of the BGP extended community. So this is what the format of route type 1, the auto discovery route. This is what it looks like. So you've got your route distinguisher. You've got your Ethernet segment identifier, which is 10 octet. You've got your Ethernet segment, Ethernet tag ID, and your MPLS or VNI. So the encoding, you know, does not change whether you're using MPLS data plane encapsulation or you're using VXLAN data plane encapsulation. The route encoding is the same. The only thing that changes is here what is actually encoded there. Here, for if it is an MPLS encap, this will be an MPLS label, obviously. If it is VXLAN encapsulation, it's going to be VNI ID. And the usages, so as I've mentioned, the type 1 route, is known as the Ethernet auto-discovery route. As I've said, there are two types of the auto-discovery route. There is the Ethernet auto-discovery per Ethernet segment, identifier, and there is auto-discovery route per EVPN instance. Both of them, they've got different usages, which I'll try to summarize. Split horizon label. The type 1 also provides faster convergence through mass withdrawal. I have a slide on mass withdrawal for you guys. The Ethernet tag ID is actually a 32-bit field, that maps either your VLAN ID or your 24-bit Vxlan ID. So there is a distinction between your Ethernet tag ID and your VLAN ID or your Vxlan. So this is actually a 32-bit field. Route type 2, this is what the EVPN route type 2 looks like. Again, as I've mentioned, this is used to provide your end host reachability. So your MAC address and or the IP of the host is actually advertised using the type 2 EVPN route. So again, you've got your route distinguisher, you've got your 10-octet Ethernet segment identifier, you've got your Ethernet tag ID, and your MAC address is encoded as part of this type, Ethernet type 2. And if the host has an IP address, that gets encoded as well. So it is not mandatory that the type 2 carries the IP address of the host. Type 3, this is what type 3 route looks like. So you've got your route distinguisher at the top, you've got your Ethernet segment, you've got your IP, and you've got your originating router IP. So again, your type 3, is actually known as the inclusive multicast Ethernet tag route. So this is what is actually used to build the the flood list. So the implication of the inclusive multicast Ethernet route is if an Ingress device needs to forward a bump traffic within an Ethernet segment, for instance, with the inclusive multicast Ethernet tag route, it will flood that packet to all remote VTEPs that are actually part of that Vxlan segment, which is not efficient. So that's why we've got a type 6, which is the selective multicast Ethernet tag route. Those are some of the optimization that that has been defined recently to optimize how EVPN, to allow EVPN Vxlan network to support multicast traffic. Again, the type 3 carries what is called the PMSI, so the provider multicast service interface, which specify how the multicast traffic is going to be replicated. These are the supported PMSI interface today. You've got your Ingress replication, which I've mentioned. There's bidirectional PIM that is supported. PIM sparse mode and the PIM SSM is supported. The type 4 route is known as the Ethernet segment route. Again, this is what is used for the designated forwarder election. This is how it's encoded today. And basically, it allows two leaves or two PE connected to the same segment to know that they're actually connected to the same Ethernet segment. The type 5 route, which is the IP prefix route, again, today, it decouples, is used to decouple the IP prefix from the MAC and IP, the type 2 route. So it's used to carry, your IP prefix. And this is how it's encoded today. There are the type 6 route, which have not included in my slide. So again, the type 6 route is, those are the optimization, that is now been defined to allow EVP and Vxlan to carry multicast traffic, so the type 6 route basically is your selective Ethernet segment route. So basically what that does is it allows, a remote VTEP to say, if it doesn't have an interested receiver to, advertise that route to the Ingress VTEP to say, I don't need to receive this bump traffic. So that will allow the Ingress PE or the VTEP to actually prune, those bump traffic. So remember, with the type 3 route, the Ingress VTEP will actually flood the multicast packet to all remote VTEP that is part of that Ethernet segment. So the type 6 route, the selective route, alleviates, or minimizes the flooding. There is also the type 7 route and the type 8 route, basically, which are used for IGMP join synchronization between the DF and the non-DF, and then the lever synchronization as well between the DF and the non-DF. So what that does at a high level is, remember, if you have two devices, your two leaves, plugging into your server, for instance, or your switch, if the switch, hatches the IGMP packet to non-DF PE, the non-DF PE needs a way to tell the DF is the guy responsible for forwarding bump traffic on the Ethernet segment. So with type 7 route, that type 7 route is used to achieve that synchronization between the DF and the non-DF. And the type 8 route is used to, if a leaf comes in, lands on the non-DF, it allows the non-DF to synchronize the IGMP leaf message to the DF. The designated forwarder, again, as I've mentioned, the designated forwarder is the device on the Ethernet segment that is actually responsible for forwarding bump traffic, on that segment. So the current algorithm, is defined as follows. So, and I'll read it to you. I will try to explain what it means afterwards. So the original DF election process elects a DF, a designated forwarder, per Ethernet segment per EVPN instance. And then it uses the following election algorithm. So basically what it does is each PE that is actually multi-ohm to a given Ethernet segment builds an ordered list of IP addresses of all the PE nodes connected to the Ethernet segment, including itself, in a numerical ascending order, starting from 0. So if I have two PEs, for instance, it will be 0 and 1. That's what that is just saying. Then each IP address in the list is then assigned an ordinal number based on its position in the list. The ordinal number starts from 0 with a value 0 assigned to the PE that has the least IP address. So the lowest IP address is assigned value 0. Then it uses this formula for a total of n PE multi-ohm to the same Ethernet segment. The PE with ordinal number 0 is the DF if the VLAN ID modulo n is equal to the ordinal value. So basically, all that is story. So basically, what that is, this algorithm was written to achieve what is called service carving. So basically, if you have two leaves, that is multi-home to a lot of servers or a lot of Cs, the idea is to, without the service carving, the lowest IP address of the leaf will actually be, elected as a DF. So what that means is a single leaf device will always be the DF. So to achieve some level of load balancing, also called service carving, they introduced this algorithm, to say, if I have two PEs, with different VLANs, try to, elect each of the PEs, per Ethernet segment per EVI, depending on the value of the VLAN ID, obviously. The downside, though, is with the current algorithm, there is an implicit assumption that the VLAN is actually, you have some level of load balancing between the VLANs. So you've got odd VLANs, you've got even VLANs. That is what the algorithm is based on. So to achieve any service carving, you need to have a mixture of even and odd VLANs. If you have, if all your VLANs are even number, the same PE will be elected. If all your VLANs are odd number, using this algorithm, the same PE will be elected. So I've tried to, do some math, plug in some value into the formula. So if all my VLANs are even numbers, 434, okay, to start with, say I have two PEs, PE 0 and 1, and all my VLANs IDs are even numbers. So I've got 434, 44, 88, irrespective of the value of the VLAN ID, as long as it's even, if I plug it into the formula, it will mean PE0 will always be elected as this designated forwarder, which basically defeats the notion of the service carving, the ability to actually have different PE elected as DF per VLAN. So to have any level of load balancing, you need to engineer your VLAN ID to be even and odd. So that is the old way of electing the DF. The updated RFC, or updated draft, to achieve that level of, to overcome the side effect or the shortcoming of the initial draft, is to use what is called the highest random weight algorithm. This is actually, I believe, was written by Microsoft in the past, and it gives you through service carving. EVPN route extended community. So here I've got a Mac mobility. So remember with Vxlan, it's an overlay network and basically allows, the whole idea is to have, to be able to move your your VM from anywhere to anywhere, any data center to any data center, irrespective of region or location. So with the mobility, how does EVPN achieves Mac mobility? It uses what is called the sequence number. So this is what the Mac mobility extended community looks like. So as mentioned, it uses the sequence number at the bottom here. So this is how the extended communities are encoded. So basically, it starts from 0. If the APE detects a Mac move, it would bump the sequence number to 1, advertise the type 2 route, and that's how the remote PE would prefer the route with the highest sequence number. That is how MAC mobility is achieved today. If there's a tie, the highest router ID flushes, its cache. The EVPN route extended community. Again, this is a transitive route target extended community that is carried as part of the ES type 4. And basically, it enables all PE connected to the same multi-ohm site to import the Ethernet segment routes. Again, limiting the scope of the multi-ohm segment route. So again, for auto, is assigned to the, attached to the type 4 route, which is used for the DF election and the auto discovery. The ESI label is actually advertised with the Ethernet auto discovery route. Is used for the split horizon filtering. Again, this is assuming an MPLS data plane encapsulation, obviously. And again, it's also used to indicate if the Ethernet segment is operating in a single active or active-active redundancy mode. With Vxlan Encap, the split horizon operation is different because we don't have the label in this perspective. So what happens is when the VTEP receives a multi-destination frame from the overlay network, it examines the source IP address in the tunnel header and filter out the frame on the local interface connected to the same Ethernet segment. So it uses the IP addresses to detect, split horizon, essentially, with Vxlan. Okay, so with EVPN mass withdrawal, fast convergence. Remember as one of the advantages of EVPN is the faster convergence we get, and this is achieved using what we call the mass withdrawal. So what happens is that if the leaves, for instance, these two leaves, 3 and 4, if operating in active-active mode, if one of them loses the attachment socket, what it does is, say for instance, behind these leaves, we're learning thousands of MAC addresses. So if leaf 3 loses this attachment socket, for instance, you don't want to withdraw all the 1,000 MAC addresses immediately. So what it does in that case, because obviously it's gonna take time, affect convergence. What it does in that case is, because each of the leaf advertise the Ethernet auto discovery route per segment, it will withdraw that single Ethernet auto discovery route per segment that is being advertised, across. And what that does is, each of the remote VTEPs or leaves will invalidate all the MAC addresses that is tied to these nest up, to the L3, to the leaf 3 nest up. So by withdrawing a single route, you achieve faster convergence. That is what is called mass withdrawal. Once that is processed, then leaf 3 can now withdraw all the 1,000 MAC addresses, for instance, afterwards. Aliasing, EVPN MAC aliasing. So aliasing is defined as the ability of a PE to signal that it has reachability to an EVPN instance on a given Ethernet segment, even though when it hasn't learned any MAC addresses. So what that is saying is, depending on the action algorithm of the the CPE, if L1, if leave 1 only learns the MAC address from this guy, what it does is it will advertise that using type 2 route, to all the remote and to this guy as well. Without aliasing, L3 and L4, we send the traffic only to L1, even though they could actually load balance the traffic to L1 and L2, because L2 is connected to the same Ethernet segment. So with aliasing, because L3 and L4, even though they've not received that same MAC address, advertisement from L2, but because L2 has already, advertised the Ethernet segment, Ethernet auto discovery route per EVPN, the type 1 route to them, they will, assume that that same single MAC address is actually reachable via both leaf devices, and they will hence load balance traffic to both of them. So that is what aliasing is in a nutshell. Distributed Anycast gateway. So with distributed Anycast gateway, so basically what this is saying is this is actually key to app suppression. So what this is saying is you can, irrespective of where the your servers are, you can have, they see the same gateway address. So it's similar to your Anycast address, for instance. So they see the same gateway IP address configured, irrespective of which data center, as long as they're part of the same VXLAN segment. The key, though, is to avoid traffic black hole, you need to have what is called the Anycast gateway MAC address. Because remember, if your VM moves from here to here, on that VM, it's got the gateway IP address and as well as the MAC address of the gateway. If that MAC address changes from one leaf to another, then you're going to have a traffic black hole. So to avoid that traffic black hole, as part of the Anycast, distributed Anycast gateway, you need to have what is called the Anycast gateway MAC address, which is basically configuring the same MAC address across your leaf device, Integrated routing and bridging. So at a high level, the RFs actually defines two integrated routing and bridging. We've got the asymmetric IRB and the symmetric IRB. This is different from asymmetric routing or symmetric routing. These are completely different things. So to avoid the confusion, the asymmetric and the symmetric IRB is just telling you how many operations is performed by the Ingress PE and the egress PE. If the Ingress and the egress PE performs the same number of operations, in the case of symmetric, they perform, route and bridge, 2 operations each, then it is symmetric. If the operation is, the number of operation is different between the P's and the C, between the 2 leaves, then it becomes the asymmetric. So basically it's the number of operation. It is not the same as symmetric routing or asymmetric routing, no. Okay, so to go into the details, asymmetric routing, so basically the operation of asymmetric routing is bridge route bridge. And with what that is doing is the Ingress PE, okay, so the Ingress PE follows the bridge route, and then the egress PE does the only perform bridging. The implication of that, though, is the Ingress PE, the Ingress VTEP, needs a way to know all the destination MAC addresses, within the network. So, which obviously is not scalable. Pretty much all vendors today actually go with the symmetric hierarchy. And with a symmetric hierarchy, the operation is a bridge route bridge approach. So meaning both the ingress and the egress devices perform the same number of operations, 2 in this case. So the ingress does 2 operations, which is route and bridge, and the egress does 2 operations as well. And the implication of that is the MAC binding, associated with an end host are required on the device hosting the first hop function, only. So meaning the first hop router doesn't need to know all the MAC addresses within the data center, for instance. With the way symmetric happens is, you have a VRF, so separate from your MAC VRF, you have an IP VRF that is assigned a globally unique VNI ID as well. And that's how you achieve the routing between the inter-subnet routing, essentially. Okay, some recommendations. So these are my personal recommendations when it comes to implementing BGP Evpn within the fabric. If traffic engineering is not required, as the case for most of the enterprise customers, I will go with eBGP in the underlay and eBGP in the overlay. Okay, so meaning, it's a single protocols, everywhere. I know, you're familiar with it. You know how to troubleshoot it. So the underlay eBGP is bound to the /31 interface IP address. Over the eBGP session, you export your loopback addresses. It's okay. You export your loopback prefixes, which is used for the Evpn overlay session. Again, as I've mentioned, no IGP is all BGP in this case. And I also recommend you have the link fault management, on the leaves, between the leaves and the spine, So what I've done here again is, within my data center, for instance, so my 2 spine, I've opted to use the same AS number. Each of the leaf pair, so, there is no requirement, or it is not mandatory that you have chassis redundancy for EVPN. But most of the customers today will ask for chassis redundancy, in which case, they will be connected into 2 leaves, for chassis redundancy. So with my setup, what I've done is I've opted for each of the leaf pair. I've opted for different AS number. And the implication of this is, I could easily reuse all my /31 IP addresses, across multiple data centers. So I can spin up any data center, quite, fast, because I don't need to, I'm not, do any addressing. I could technically just reuse the /31 IP address across multiple data center. The only thing that is changing, obviously, is the AS numbers, here. And lastly, I think I need to stress, with the setup, it is a lot easier to template your configuration. So your layer 2 VPN configuration template becomes, easy. Your layer 3 template is easy. So now you can, using Ansible or whatever, you could template your configuration and, deploy services, a lot faster. My test topology, this is what it looks like. So I've got again, these are all Arista configurations. So I've got a pair of leaves here, here. So the left-hand side is one data center. The right-hand side is another data center. The Cisco here at the top, these are, you can, think of it as a bordered device or bordered leaf, for instance, or whatever. So that's my one link, connecting the two data centers. And the whole idea is to have an L2 service here or L3 service and provide connectivity across the data center, irrespective of the geographical location of those data center. So here, this is what my configuration looks like. So for my spine, again, I've opted for the same ES number in the spine. Okay, so all this is done on the Arista VEOX. So define my neighbors in the underlay. Again, so this configuration is only specific to the underlay. So again, underlay is eBGP over the /31 physical interface. So this is basically what I'm doing here. But the key though is because I'm using the MC lag, I need to have an eBGP sessioner over the MC lag between the leaf pair as well. The allow AS2 is needed for some corner cases, where you have a double failure in your link between the leaf to the spine. So again, it's vanilla eBGP configuration, here, it's just what you used to today. Key though, on the Arista, I found out without enabling the service routing protocol model multi-agents, your EVPN is not going to be active. So this single line is key to have to activate EVPN. This is the verification for my underlay. So again, remember underlay is just native eBGP over the /31. You could see my show IP BGP summary and on the leaves and on the spine. So on the leaf, I've got two eBGP sessions to the two spines. And from the spine perspective, I've got all these are 4 eBGP sessions within that data center to all the 4 leaves I've got in there. Show IP BGP routes for the underlay verification. So again, these are just the loopback addresses I've injected, into the underlay to enable me to establish EVPN BGP in the overlay. So for the overlay configurations, this is what it looks like. Remember, with the overlay configuration, my pairing now is to the loopback addresses which I've advertised in the underlay. Okay, and here, address family EVPN. This is how I activate my EVPN address family on the Arista, and to ensure that I don't have to, multiple routes floating around, I need to disable the pair group, for instance, for IPv4. So for this pair group, I only want to advertise EVPN routes. So it's only used for EVPN. And again, you can see the configuration is pretty straightforward. This is the beauty of having eBGP, in the underlay and in the overlay. You can template your configuration. This same configuration, with little modification can be deployed in other data centers straight away. This is the leaf configuration. Again, it's similar to the spine, with the leaf overlay configuration, just pairing to the spine loopback addresses, and again activate our EVPN address family. There's a key point though that you need to know. Because this is eBGP in the overlay and the eBGP in the underlay. For the overlay, you need to, this line is key. Remember, your eBGP will rewrite the next hop information. So on the spine, it is critical to have the next hop unchanged to ensure that your spine does not sit in the forwarding part. Actually, it's going to break if you don't include next hop unchanged in your configuration. So this is only needed on the spine to ensure if for the EVPN route, when they leave, when the spine advertise those EVPN routes, learn from one leaf to another leaf, it doesn't rewrite the next hop information. So this is actually key, otherwise your configuration is going to break. And this is how you validate your overlay outputs. Again, is show BGP EVPN this time around on the leaves. It's got two eBGP session to the loopback addresses of the spines. And from the spine perspective, again, is the same, output, but 4 in this case to all the leaves. Detail output is this. So here, I'll have another slide that shows it. So this is your inclusive multicast Ethernet tag route type 3. This is your type 5 route. This is what it looks like. So these are the EVPN routes, and the command is show BGP EVPN. So these are the EVPN routes. So MAC addresses, type 3 route, type 4 route. In this case, I won't have any type 4 route because it's, I'm using the MLAG. So with the overlay configuration and validation out of the way, we now layer services on top. So I want to, build an L2 VPN, for instance. So with L2 VPN, it's straightforward. The key is you defined your, VNI for that particular VLAN ID. So here I'm using 128, and you remember the VNI needs to be globally unique. That is the key here. It needs to be globally unique. And once you have that going, the other thing you need is from your sorry. Okay, I'm not showing the BGP configuration, but this is what the BGP configuration looks like. Let me quickly show you. So this is once you define, so on the Aristar VOX, you define one configuration on the VXLAN, the other configuration under the BGP session. So this is how you tell BGP to actually advertise, the MAC addresses for these VLAN ID, VLAN ID 28 here, for instance. So again, you can see the configuration is pretty straightforward, just 3 lines defining the route distinguisher, the route target, and then, redistribute line MAC address. So with this leave, all MAC addresses learned from VLAN 28 will get injected into, will be converted in, will be carried via BGP and advertise to, across the data center. And that's how you achieve L2 connectivity end to end. So irrespective of the geographical location, any host in this VLAN 28 can have L2 connectivity across board. And if you need L3 connectivity for the same VLAN, again, it's a matter of just, this is how you achieve the symmetric IRB in this case. So with a symmetric IRB, again, you define your VRF, okay, your route target, and, I'm redistributing connector, meaning my SVR interface. So this is my SVR interface here. So here, so for symmetric IRB, you need to assign a separate VNI for the IP VRF. So this, to achieve inter-VRF or inter-subnet connectivity, under the Vxlan, for the Vxlan encapsulation, I defined my separate VNI that is attached to that VRF 28. Remember that VNI is different from the one I used to achieve layer 2 connectivity. So this Vxlan VLAN 28 VNI 128 is just for L2 connectivity across data center. For L3 connectivity, for symmetric IRB, you need to assign a globally unique separate VNI and map it to the VRF. So, and again, move on to your inject the same in your BGP, and that's how you have end-to-end L3 connectivity. So here I'm importing. So if I want to provide connectivity between VLAN 28 and VLAN 30 or VLAN whatever different customer, it's just a matter of importing those route target here, and from BGP I will receive those routes and then get imported into these VRF. That's how L3 connectivity. So that is today with Vxlan encapsulation. This is how you achieve L3 VPN that you have in IPN PLS today. So with IPN PLS, you've got your VPLS for L2. You can achieve the same, with EVPN Vxlan, using, maybe 5 lines of configuration, which is a lot easier to template. And then for L3 VPN, you can have connectivity between any VRFs by just importing the route target assigned to that VRF. Okay. Okay, this is what the type 2 MAC route looks like. So you've got your RD. Remember I was showing you the encoding, the route encoding. You've got your route distinguisher. You've got your MAC address here. So again, as I've mentioned, the MAC IP, the MAC route, the type 2 route, you've got two. You've got the MAC and the IP and the MAC address itself. Okay, so you can see you've got the first one does not have an IP. The second one has an IP address. Both IP and the MAC address. And again, here is more route from the lever perspective. To look at the MAC addresses, again, is show Vxlan address table VLAN 28. So this is showing me all the MAC addresses, the remote MAC addresses, actually, that I've learned. And here again, show Vxlan address table EVPN VLAN 28. So he's saying this MAC address is of EVPN type, using Vxlan encapsulation in the data plane, and the remote VTEP is this guy. For the L3 VPN, in the context of EVPN, it's just a matter of show IP route VRF, that particular VRF. So this will show you all the routes, L3 routes, for instance, both remotely and the ones I've learned are locally. So this is not different from your IP VRF today. Okay, that concludes the configuration walkthrough on EVPN, Vxlan, data plane encapsulation. Any question? I've got maybe 2 more slides. This is just to go through some legacy. How do you migrate a legacy platform, for instance, to EVPN Vxlan? So here, what I'm doing here, I've chosen Juniper Q Fabric, and then to migrate that Juniper Q Fabric, to EVPN Vxlan design. So to put things in context, so again, the Juniper Q Fabric is actually an Ethernet fabric, so meaning it has a lot of it's got a lot of moving parts, actually. It's got its control plane. It's got the IC, which is acting as the data fabric. And it's got a lot of the leaf devices are called the RSNG for, if they're redundant, or server node group. And it's got the NNG, which does the layer 3 functionality. So what I'm doing here is migrating services off these legacy platform onto VPN, Vxlan EVPN design. So here, again, what I've done is pretty straightforward. I've have a dedicated border leaf connected to the legacy switch. So this can be any legacy platform, to be honest. Have it trunk down. So here, what I've done is on the border leaf, each of the SVI now sits in a separate per customer MAC VRF, and connectivity between those MAC addresses learned, over that trunk interface on the border leaf to all the leaves is done over Vxlan EVPN. So from here, I could have connectivity to any of the services, layer 2 services, hanging off the Q fabric within the same data center. For L3 services, again, I need a way to be able to learn EVPN route from remote site. So what I've done in this case is mostly, your switch will be connected to your router devices. So I have a link up to the DCI, your router device, and basically I have a separate BGP VPN session over that. And in addition, depending on your setup, if you have multiple VRFs on your router, again, you need 802.1q link. I'm using the same link anyway. And then each of those will land in a per customer VRF. So at a high level, this is what I'm doing. So configured per customer SVI or IPVRF eBGP session between the QFabric NNG to the border leaf device. Okay, and to allow for smooth decommissioning of the fabric, so I've got 2 eBGP sessions actually. one between the NNG and the border leaf, and then another one between the border leaf and the DCI. So I could then play with the BGP attribute to decide how my data is going to flow. Do I want to go through the DCI, or do I want to go through the QFAB? So DCI and the QFAB sends a single default, over that eBGP session per customer, per VRF here. And then between the border leaf and the leaves, again, is Vxlan Evpn, so that connectivity is maintained. If I need to go out to the other data center, I'll go over the eBGP BGP VPN session to the DCI, and that's how connectivity is achieved. And this is what it looks like post-migration, and this is me. So thank you so much. Special thanks to these guys, Cisco Press. These are some of the references I've used. The Juniper QFX book written by Douglas Richard. And then thanks a lot. And these are all the references. Any questions? Yes, sir.